Let's jump right into this explainer. If you've been working with distributed systems, you know Apache Kafka has essentially been the undisputed backbone of real-time data streaming. But what we're looking at today is a monumental shift. Between version 4.0 and the newly released 4.3.1 here in 2026, Kafka hasn't just seen a few minor updates. No, it has undergone a complete, ground-up architectural metamorphosis. We're talking about a fundamental re-engineering that finally turns Kafka into a truly cloud-native system. Okay, let's dive into this. We'll start by looking at the overarching cloud-native metamorphosis, and then we'll break down the three pillars of this new architecture. Pillar 1 covers KRaft and metadata. Pillar 2 is all about diskless topics for storage. Pillar 3 dives into share groups for compute, and we'll wrap up by looking at what this cloud-native future means for all of us. Section 1, the cloud-native metamorphosis. So, to set the stage for 2026, Kafka 4.3.1 is really the culmination of over 25 KIPs. They've ironed out some notorious wrinkles, like that RocksDB native memory leak, to make the platform incredibly stable. You know, historically in 3.x, compute and storage were tightly coupled to local disks, right? You had these strict consumer limits that forced you to over-provision, and on top of that, you carried the heavy operational burden of managing external metadata. Well, today, state, storage, and consumption have been completely re-engineered from the ground up to solve those exact bottlenecks. Pillar 1, KRaft, and the metadata layer. So here's the massive news. As of Kafka 4.0, ZooKeeper is just entirely gone. The standard is now KRaft, or Kafka Raft. Think of it as Kafka's internal consensus mechanism. Instead of pushing your cluster state out to a separate external ensemble, all your metadata is now managed by a quorum of controller nodes living entirely within the Kafka ecosystem itself. It uses the Raft protocol to ensure strict consistency, completely replacing ZooKeeper. The operational advantages between the legacy ZooKeeper setup and modern KRaft are absolutely staggering. Back under ZooKeeper, if a controller failed, the new one had to load the entire state from that external system, and that caused failover latencies of anywhere from 5 to 30 seconds. But under KRaft, standby controllers are constantly replaying the metadata log locally. This drops your failover latency down to literally under 1 second. Less than a second, even if your cluster is managing millions of partitions. Now, if your team is planning to migrate from 3.x to 4.x, you have to run KRaft as a prerequisite before the upgrade. You'll evaluate your cluster, size your controller quorum, which is usually 3 or 5 dedicated nodes, and run in dual mode to validate that metadata sync. But pay really close attention to step 4 here, JMX metric updates, because the legacy metric namespaces change entirely when you move from ZooKeeper mode to KRaft mode. You absolutely must thoroughly review and rewrite your dashboards and alerting rules before you go ahead and decommission ZooKeeper in step 5. Pillar 2, diskless topics for storage. Now, what's really interesting about this slide is KIP 1150, which introduces diskless topics. This is a brilliant leaderless architecture where your brokers write data directly to object storage, think Amazon S3 or Google Cloud Storage, completely bypassing local disks for persistence. In traditional Kafka, all partitions have a really strict leader-follower model, but diskless topics introduce a leaderless, zone-aligned internal structure, so any broker can accumulate requests in a buffer and then upload those complete batches straight into the cloud. It's a real game changer. If you look at this storage evolution, the leap is massive. We started with local SSD only, right? Which was expensive and had super slow recovery because data had to replicate over the network. Then came tiered storage, which improved things by mixing hot local and cold S3 storage for better cost and speed. But diskless topics, they take data locality to remote only. Your brokers carry virtually no state. That makes scaling and recovery effectively instant because it relies purely on metadata updates rather than shifting terabytes of data around the network. And the real-world impact of that architecture? We're talking about an incredible 80 to 90% reduction in total cost of ownership. No way, right? But it's true. Why? Because standard Kafka setups force you to replicate data 3 times across different availability zones, just to ensure durability. And you know, cloud providers charge heavy egress fees for that cross-AZ traffic. By writing directly to object storage, which handles its own cross-region replication for free, all those AZ networking fees completely disappear. Just to put those percentages into perspective with some hard economic numbers, if you're running workloads at, say, 1 gigabyte per second throughput, your infrastructure costs can drop from roughly $1 million a year down to just $100,000 a year. Let that sink in. Diskless Kafka is an absolute paradigm shift for business outcomes. You get instant elasticity, zero client changes, and massive cost savings. The only real trade-off is a slightly higher request latency.
Pillar 3. Share groups and compute.
So this brings us to KIP 932 and share groups. This is a consumer model that allows multiple consumers to cooperatively process a single partition via message-level acknowledgement. For years, if you needed traditional queuing semantics, like the kind you'd find in RabbitMQ or SQS, you had to run a totally separate system right alongside Kafka. Well, not anymore.
If we frame this new feature against the legacy 3x behavior, the contrast is stark. Classic consumer groups enforce a strict one consumer per partition rule. If you have 10 partitions, you max out at 10 consumers, period. To scale up during a traffic spike, you had to over-provision and create hundreds of partitions in advance. Share groups literally throw that limitation out the window. You now have record-level assignment, which means hundreds of consumers can pull from a single partition simultaneously. The trade-off is the loss of strict ordering, sure, but for long-running tasks or massive parallelization, you eliminate head-of-line blocking entirely.
Now, you might be wondering, how does it manage this without blowing up the broker's memory? Well, Kafka uses a brilliant sliding window architecture. A share partition leader tracks in-flight records using two markers. First, the SBO, or share partition start offset, which is simply the earliest message not yet acknowledged. And second, the SBEO, or end offset, which is the latest available message. This sliding window allows Kafka to coordinate high-speed parallel delivery without having to track the historical state of every single record that has ever existed in the log.
And this brilliantly illustrates the life cycle of a single message. Within a share group, a record starts as available. When it's fetched by a consumer, it becomes acquired and locked for a set duration, so no one else processes it. Once processed, it's acknowledged. But what if you hit a poison pill? A bad record that completely crashes your consumer. In the old days, that would stall the entire partition. Now, if a record fails a specific number of times, it's automatically marked as archived. It's essentially moved out of the active path, allowing your system to seamlessly continue processing the rest of the queue.
Section 5, the cloud-native future. So the crucial point is really captured right here. Kafka has achieved the operational simplicity of a single binary deployment, the flexible scaling of a message queue, and the cloud-native economics of object storage. It's truly a fully unified, incredibly elastic data platform ready for massive real-time demands. But with storage and compute now completely decoupled, it leaves us with a fascinating question. Is Kafka still just an event streaming platform, or has it quietly become the ultimate universal database for the cloud era? If you need notes and Q&A, please DM me on Instagram and I will share the entire notes.